everybody, welcome to another video. We're talking about stoichiometry, and in this video we're going to talk about relative or average atomic masses, relative molecular or formula unit masses, and what kind of questions can you get from this subtopic of stoichiometry. So let's get right into it. We will start with defining what the average atomic mass is, and like I said, it could also happen in the exam, you're asked about relative atomic mass. So average and relative are two terms that are used pretty interchangeably. So don't get afraid if the term relative is used instead of average. So the average atomic mass, represented by A subscript R, is the average mass of an atom of an element compared with 1/12 of the mass of carbon-12 atom. This value is a ratio and thus has no units. So why do we have average mass of an atom written here? Remember that there are different isotopes within the same element. So by taking the average mass of an atom, we're taking into account all the different isotopes that are present. So the average mass of an atom would basically be the sum of the mass of isotopes over the number of all isotopes. We're using carbon-12 atom as a standard here. बहुत पहले hydrogen use किया जाता था, but then the mass of carbon-12 atom was the one जो कि most accurately determined किया गया है अभी तक, and it has it's like 12.000000. So it's the most accurately determined mass right now, and that's why it's used as a standard. So the average, that's the definition of the average or relative atomic mass, AR. And then we have the average molecular or the formula unit mass. So molecular mass, a relative molecular mass would be for covalent and for covalent compounds, and formula unit mass, relative formula unit mass would be for ionic compounds. So the average molecular formula, the average molecular mass is the mass of a molecule compared with 1/12 of the mass of carbon-12 atom. And the mass of the relative formula unit mass would be the average mass of a formula unit compared with 1/12 of the mass of carbon-12 atom. Basically, in summary, the average molecular mass would be the sum of all the relative atomic masses of all the atoms present in the molecular formula, and likewise the relative formula unit mass would be the sum of all the relative atomic masses of all the ions present in the in the formula unit. Now, you guys, some of you might wonder that acha ion ka mass or atom ka mass same hi hoga. I want you guys to recall how electrons ka mass is negligible compared to the mass of protons and neutrons, and therefore changing the electrons does not change the mass considerably, or up to a point that you can notice it. So at this point, the relative atomic mass of an atom would be the exactly the same as the respective ion, so don't worry about that. All the relative atomic masses are given in the periodic table, so you don't need to worry about calculating the relative atomic masses. All you need to do is look at the molecular or the formula unit of the compound that you're looking at, and then just go to your periodic tables and identify the ones that you need and use them. Now here, I'd like to point out that the relative atomic mass is very close to the nucleon number. Now, the only difference is that the nucleon number is simply the sum of protons and neutrons present in the nucleus, and so it's an integer, it's a whole number value. But the relative atomic mass, since we compare it, we take into account all the isotopes, and we also divide it by 1/12 of the mass of the carbon atom, so it's a more standardized and more formal, and it will be in decimal points, it will be in points, it will not be in a whole number. Well, it can be, but most of the times it will be in decimal, so keep that in mind. But overall, it will be a very, very close value. So let's look at a question. You could be asked of this question in an MCQ. In fact, this is one of the questions in the past papers, and the a question asked for the relative molecular mass of MgSO4. So what we do is that we just look at the periodic table and we fish out the atomic mass of magnesium, which is 24, the atomic mass of sulfur, which is 32, and of oxygen, which is 16, but there are 4 oxygen atoms here, so we multiply that by 4, and 120 would be the molecular formula, the relative molecular mass. Now, this will all depend on the kind of periodic table you're given. If the periodic table that you are given has the ARs and MRs in decimals, then you should know that this is very accurate and they're writing relative atomic masses. But if it is in whole numbers, and most likely they're not being very accurate, and they're just writing the nucleon numbers. So you don't have to worry about anything. You just have to work with the periodic table that you're given and you're good. So this is not your headache. It is the headache of Cambridge. And you'll just use the periodic table that you're given. Now, there's another thing. The percentage composition that can be determined. Now, this is a question from the past paper, and I thought that this concept would be better explained if we just look at a question. So they are asking you to determine which oxides, Fe2O3 or Fe3O4, have more iron. So what you do is you will determine the percentage mass of iron in both of the oxides and then compare. Now, to calculate the percentage mass of the iron, you will need the AR of all the atoms of iron present in that particular molecule, and then divided by the total relative molecular mass of the oxide, and then multiplied by 100. So in case of Fe2O3, first we start with calculating the MR. We have 2 iron atoms, so 56 into 2, and then we have 3 oxygen atoms, so 3 into 16, and the total will be 160. For the percentage, we have 2 iron atoms, so we write 2 into 56. The total molecular mass is 160, and we multiplied by 100, and we get 70%. For Fe3O4, we calculate the MR, which is, we've got 3 iron atoms, so 3 into 56, 4 oxygen atoms, 4 into 16 is equal to 232. The percentage of iron would be then 3 into 56, which is 3 atoms of iron, and then over the molecular mass, which is 232, multiplied by 100, and you get 72%. And 72% is clearly greater, not much, but greater than 70%. And so Fe3O4 has more iron. That's how you solve for questions that involve percentage compositions. It could also be that your past paper questions ask you to calculate the mass of an element in a compound. So this is also a past paper question, and in this one they're asking you, what is the mass of iron in 200 grams of Fe2O3? So to solve this kind of question, your step 1 is to calculate the percentage composition, and in the step 2 you just multiply that percentage composition with the given mass. So here the percentage of iron would be, there's 2 atoms of iron, so 2 into 56, divided by the total molecular mass, which would be, it has 2 iron atoms plus 3 into 16, and you get 70%. And this is something that we calculated in the previous question as well, so we're using the same compound. In the step 2, we take this percentage and we multiply it with the given mass. So they want us to look at the percentage, the mass which is present in 200 grams. So what we do is 70 over 100, 70% of multiplied by 200, and it would give us 140 grams. So there's 140 grams of iron present in Fe2O3. Then the next kind of question that can come from this topic is that they want you to calculate the mass of water in a compound. Now, certain compounds have a hydrated version, and they've got some water molecules attached next to their formula unit, and these are mostly ionic compound. So in this particular past paper question, they're asking you to calculate the water mass in 12.5 grams of hydrated copper sulfate, and this is the formula that is given. At this point, they will not really expect you to write know the number of water molecules that are present in the hydrated copper sulfate. They would give you the formula, so you don't need to worry about that. You only need to worry about how to calculate the percentage, and that's literally the same thing. You know that the mass of H2O is 18, 2 plus 16. So AR of 5 H2O molecules, because there are 5 H2O here, and then the total mass of the copper sulfate dot 5 H2O. And this dot is just a representation of how you write a hydrated compound. So you write the normal formula, you put a dot, and then you just add the number of water molecules that are present in that in that thing. Okay, so coming back, you take the mass of the total water molecules, you take the mass of the overall molecule, and then you multiply it by the mass of the sample. Now, first you could also go through the route of multiplying it by 100 before and first calculating the percentage composition of water, and then multiplying it with the given mass. But essentially this is exactly the same thing, because you multiplied by 100, but then you'll have to divide by 100, so it just cancels out. So in this question, I have skipped that thing and just multiplied it directly with the mass of sample, and that is 5 into 18 over 250. 250 is the overall mass of this compound that I calculated. And you multiplied with the given mass, which is 12.5, and you get 4.5. So there is 4.5 grams of water in 12.5 grams of hydrated copper sulfate. That's about it for this video. I hope that some of the things that we discussed, and actually all of the things that we discussed in this video, are pretty clear. I'll see you in the next one. Take care of yourself.